Okay, so we've seen that means and standard deviations can be extremely useful ways of summarizing a bunch of numbers and nicely reducing that diversity of numbers down into two quite simple numbers. One which tells you how typical a person is, and the other one tells you how diverse the group are. Really useful things. However, there are limits to these, and these limits are very important when we start considering parametric assumptions. Essentially, one of the things about parametric assumptions is if you can use a mean on it legitimately, you can do a t-test on it. That's kind of all it means, but let's see why it's a problem. Data that's normally distributed is really what we want in order to use means and standard deviations, so that's kind of a precondition. And also we don't have scores in there that are too extreme, so-called outliers. So as we probably know, many kinds of measurements you can do on people: height, weight, IQ, shoe size. If you take those measurements of a bunch of people and put them in order, so we've got the lowest score, the smallest shoe size, the lowest IQ, the lowest weight, the lowest height, to the highest, and if we order them like that, then what we have is something like this, the normal distribution. So the y-axis, so the x-axis along the bottom here, is simply how big somebody's feet are, how tall somebody is, how high IQ is. So we've got very high IQ, very tall people over here, very short people or very low IQ people over here, and the y-axis up here is simply how many people fall into that particular category. Now what the normal distribution says is that for things like this, most people are about average. The majority of people are average. Which makes sense, you know. The average is supposed to be a measure of typicality. We want most people to be average. If most people weren't average, then the average, the mean, isn't telling us anything about what the typical person's like. Yeah. So this is the distribution we have here. So these are the tails here. I think I've got this on the graph. These are the tails. So we can see that very few people are very tall. On the right hand side here, very few people are very short or high. Very few people have very high IQs. Most people are clustered around the typical average person. If we look at the standard deviation, because every mean for anything that has a mean as a standard deviation, then the properties of a normal distribution says that plus and minus one standard deviation from the mean, struggling with words today, that 68% of people are within plus and minus one standard deviation. If we look at plus and minus two standard deviations, it shoots right up to 98% nearly. And then plus and minus three standard deviations, it's 99.7%. So you can see that most of the people are clustered in the middle, which is why the mean does represent a good measure of typicality when our data are normally distributed. But however, if some scores are very high or very low, if we have some very big scores or some very, very small scores, then this can have a big problem in the way that it affects the mean. So let's look at these two scores here. We've seen these two groups before, but I've just fiddled with them so that instead of so two of the numbers have been replaced in the left-hand group, the right-hand group remains the same, and I've just simply given somebody 100 and somebody 90. So we've got two very extreme scores here. Now, what does that do to the mean? Now, remember before, the mean was something like 13 point something, which was pretty typical of the average person. These big scores are now having the effect of dragging the mean up, so it's now 24.6. Now, if you look at those scores, is that typical of anybody? Well, no, because nobody scores, apart from the two extreme scores, nobody scores over 19. That's the highest score. So 24.6. If you were trying to say, well, use that as a representative of the typical person, and you look at those scores, it's not like anybody. It's not like any of the normal numbers there because it's too big, and it's way smaller than the two really big numbers. So suddenly the mean becomes unrepresentative. So you shouldn't use it because it's no longer typical representative of typical score, unlike on the right hand side, which haven't changed, in which 11.6 is, you know, relatively representative of the typical person within that particular group. So these are known as outliers because nobody scores anywhere near 24.6. When you get these kind of things, it's no longer useful to use the mean as a measure of typicality, and it's no longer sensible to use a standard deviation, so we have to then default to using some other kind of measurement. One kind of measurement is the median, which is it insensitive to these big scores because it simply uses the ranks. It doesn't care about the numbers as values. It just says, well, okay, 9 is the smallest number, 10 is the next smallest, then 11 is the third smallest, and 12 is the fourth smallest, and then 12 again. It treats them as ranks. And all we do is we find a middle place here, sort them in order, smallest to highest. We find the middle one, which is 14, and that's now the median. Now 14, again, is unaffected by these big scores. The median would be 14 if 90 there were replaced by 20, and if 100 were replaced by 21. It would still be 14. These scores have no effect, which means that it's a good way to represent data when you've got these big problematic scores like this, when you've got outliers. There are other ways of dealing with that, we'll see in a second. So 14 now, so the median, and that's pretty similar to the 13 point whatever it was, which was the mean that we got in the first time we do this without the big scores in there. So the median is useful. So in terms of outliers, one of the ways in which you may have been taught to look for outliers is by use of box plots. Now box plots are kind of very curious things, and there's plenty of exercises on box plots on the website, and there's screencasts on how to generate box plots, as screencasts on how to test for outliers on there. But let's just go through basically what we have here. What we have basically is a box. Now the top and bottom of the box are called hinges, and this is trying to represent something about the deviation of the scores. It's a bit like a normal distribution curve. You imagine looking down on a normal distribution curve from the top, like an aerial view. This is kind of similar to what we're looking at, with these being the tails, the top and bottom things, here being the tails, and this being a kind of big bulbous bit in the centre. But they're kind of non-parametric because they don't use means and they don't use standard deviations like normal distribution representations do that we saw earlier. They use non-parametric scores such as medians. So but the big line here is a median. The thick line here, this is the lower hinge. This represents the interquartile range. So this is the first quartile, this is the third quartile, and the upper caps here are 1.5 times the interquartile range. This, you can tie yourself up in knots understanding this, but I'm just trying to get a feel for what it is. I'm not expecting you to know all this sort of stuff. You're certainly not going to be asked about it. But it's just a way of representing spread. And this is the box plot. Other box plots look like this, so you can get something to feel. This one here, this second one here, you can see this is quite normally distributed because everything's nicely kind of symmetrical. This is reasonably normally distributed here, this one here, MA. This isn't too bad. But we can see that some of these, like this one for example, this one here, the whisker here is very big for the lower scores, but relatively small for the upper scores, which might suggest that this is getting a bit kind of skewed. But let's forget about skewness for the moment, because what we're interested in at the moment is outliers. Now outliers, or at least potential outliers, let's be careful, identify themselves on box plots by little circles here outside the range of the box plot itself. So outside 1 plus and minus 1.5 times the interquartile range, which remember are what the whiskers that represent, that limit. So this is somebody lying well outside the kind of normally accepted levels of what is a reasonably normal score. So this might possibly be an outlier. The trouble with that is so if you find a circle in a box plot, if you find any circles, it suggests there might be outliers. The trouble is it gets very impressionistic. We're kind of left very much into the kind of subjective interpretation. Is it an outlier or is it not? Somebody might look, oh, it's an outlier. Somebody might think it isn't. So there is a more technical way of doing it. The kind of technical statistical way is that if a score is more than 3 standard deviations away from the mean, plus or minus, then we would consider that to be a troublesome outlier, and we should certainly give it our attention. What that attention entails, I'll tell you in a minute. So, for example, it's actually 3.29, but, you know, about 3 standard deviations away from the mean. How might we do this? Well, the easiest way to do it is to turn each score into what's called a Z-score. Now, a Z-score is simply, if we've got a bunch of scores, I thought I had an example here. I'll move back. If we got a bunch of scores, then a Z-score simply says how far is each score away from the mean in units of standard deviations. And SPSS can do this for you, and it shows you how to do it on, if you go into the box plot area of the website, there's a little screencast showing you how to do this, and there's an exercise which gets you to do it yourself. So it simply says how far is each score away from the mean, like we saw with standard deviations. How big is that deviation, but how big is it in terms of standard deviations? Okay, so a z-score of 0 means that the mean, that the score is exactly the same as the mean. Right? There's no deviation from that score from the mean. It's 0. It is the mean itself. It's the same value. A z-score of 2 for a particular score means that particular score is 2 standard deviations above the mean, and a z-score of say minus 3.5 means that the score, that particular score, is 3.5 standard deviations below the mean. So this is one way of trying to identify real outliers in a more systematic way than simply looking at dots and making some random decision about it. How one deals with outliers is a matter of some debate. Once you've identified them, once you've found that they're over 3 standard deviations away from the mean, some people think let's just delete it, let's get rid of them. But the trouble with this is that this is data, this is somebody's score, and simply removing people's data because you don't fit in with some kind of, idealized view of what you should be getting, a lot of people would say, and I would agree with them, is problematic. So just deleting them is a problem. The only reason you might be able to delete them is if you genuinely believed and had good evidence to suggest that that person's score was an anomalous score. For example, they didn't read the instructions properly, they weren't taking it seriously, they had forgotten their glasses so couldn't see the stimuli, or whatever it was. That's the only reason you can actually genuinely remove something. Okay. Another way of dealing with it, which again some people would say is a bit tricky, but this is, if you're ever in this situation, discuss it with your supervisor, because there is debate. The other one is that you replace any outliers with 1 plus or 1 minus the next highest or lowest score. So let's say we have a score, some data which is 1, 3, 4, 7, 12, where 12 in bold is the outlier. We identify that as an outlier, then we can replace it with 1 plus the next highest score, which is 7. So we add 1 to that, it becomes 8. So the scores would now be 1, 3, 4, 7, 8. Similarly, if we had a very low outlier, which is 3, 12, 17, 19, which 3 is the outlier, we find the next lowest score, which is 12. We take 1 away from it, which gives us 11. So now the data would read 11, 12, 14, 17, 19. So you would actually change the numbers in SPSS itself. But you must report you did this. Now you might be tempted to say, well, hey, I don't need to do this. What I could do is simply use a non-parametric test. I could use a Wilcoxon or a Mann-Whitney. I don't need to use a parametric test because parametric tests are okay to use with outliers. The trouble is that that's pretty much what a non-parametric test does, because it treats the numbers as ranks. It does exactly the same thing anyway. It just essentially removes these very big numbers and just turns them into ranks, as we saw in the slide when we talked about the median. Okay, I'll stop there, and then the next one will be on skewness.